everyone, this is Hui. I am an assistant professor at the Computer Science Department of UMass. I'm going to present one of our recent work on accelerating RNN-based sequence modeling applications. RNN is short for Recurrent Neural Network. It is one type of deep learning model that is very good at sequence modeling. For example, in the next word prediction task, you can use RNN to predict what is the next word you are going to type. After feeding the model with the inputs, we are going to discuss recurrent. The model may be able to predict neural as the next word. So when the next word, neural, is already typed in, it will feed into the model to predict the coming word as networks. Besides the network prediction, RNN is also applied to other data sequence-based applications. For example, it can handle function call trees to predict the next function call. This can help with the compiler optimization. It can also be applied to memory access sequence for data prefetch. Some other sequence-related tasks, including system log analysis to predict the system failure, user activity analysis for personalized recommendations, and others. Although RNN is very effective in many sequence modeling tasks, the effective adoption of RNN faces two main challenges. First of all, we want the prediction to be as fast as possible. Take the next word prediction task as an example. Suppose you are using RNN for prediction of next word. If the next event is already arrived, even before your model can give you the prediction, then even though you have the prediction available, it won't bring any benefits. Besides the performance requirement, sometimes we also want to predict the next sequence of events instead of the next single event. For example, we can predict the next two words, neural networks, instead of just the neural. A larger prediction scope is more important if your application takes more time to handle the predicted results. For example, if you can predict the next several function calls, you can have more time to perform runtime code optimization to functions that run super slow. If you can predict the future events that are going to happen on a server based on the system logs, then you may have enough time to prevent a system failure. A larger prediction scope can usually give you more time to plan for actions for other user activities and other data sequence. To address the about two problem, our basic idea is to learn on compressed input sequence instead of the original sequence. A lot of data sequence contain repetitive patterns. For example, they are going to discuss may often appear together. We can reduce it to a single symbol. We can apply data compression to the input sequence to get its reduced form, the compressed inputs, and feed these inputs into the RNN model. Because the input data sequence to consume is much shorter, we are able to reduce the time to make our prediction. When we make a prediction, the predicted symbol can be a sequence of events instead of a single one. This can also help us increase the prediction scope. To see how we are going to apply this basic idea, let's first revisit the typical workflow of developing an RNN-based application. The workflow has two steps. One is offline RNN training, another one is online inference. So in the offline training, you will train an RNN model using your training inputs and your training targets collected offline. Then the model is deployed to handle streaming inputs and then make predictions. To apply compression to RNN applications, the first question to answer is how to compress the training inputs. And the second question is how to perform inference on streaming inputs. Next, I will talk about each of the challenge and its solution in detail. Let's look at the first challenge. So the tricky part about applying data compression to training data is to keep the statistical properties of the sequence such that the RNN can still learn patterns from the compressed sequence. Our solution is grammar-based compression and accuracy-conscious lowering. Grammar-based compression is related to context-free grammar. The CFG is a formal grammar that consists of production rules. The example here shows a production rule. It means the symbol 1 can replace the string ABC. The left-hand side is usually a single non-terminal symbol. The right-hand side is a sequence of terminals and non-terminals. Grammar-based compression aims to transform the input sequence into a context-free grammar. Let's look at an example. Given this sequence, we can apply a grammar-based compression algorithm called separator to produce a list of production rules. So the first rule shows the most compressed form of the input sequence. If you keep applying the other rules to extend the symbols in the first rule, you will get the original sequence. However, this most abstract form is not friendly to training at all, since it contains many symbols that appear only once or twice. To solve the problem, we apply accuracy-conscious lowering. Its basic idea is to keep expanding the first rule until all the symbols in the sequence have a frequency that is larger than our threshold. We identify the threshold using binary search to meet the accuracy requirements set by the user, such as 0% or 1%. Now we have finished our first challenge. So after the first challenge is resolved, the online training will give us a well-trained RNN model that can compress the sequence as input. There is also a dictionary that encodes the meaning of each symbol used in the sequence. The next challenge is how to conduct online inference given that the input streaming inputs are not compressed at all. Our solution is tokenization with rollback. Essentially, the basic idea of tokenization is to replace our subsequence of events in the streaming inputs using symbols in the dictionary, while rollback tries to fix the problem caused by the nearsighted property of tokenization. It will roll back hidden states of RNN to undo the state changes when necessary. To understand the mechanism, we need to dive into the details of how an RNN makes a prediction. RNN is composed of recurrent units that continuously transforms the input hidden state to output hidden state. Prediction is made based on the hidden state. Next, I will explain how does tokenization with rollback work using an example. Let's see, at time t equals to 1, we have an input x. We use a tokenizer to compress the streaming inputs, and we get x as the output. After feed it into the RNN, we get a prediction that is 3, which means a sequence of ABC. And the hidden state is transformed from H0 to H1. At another time step, a new event is ejected. The tokenizer produces A as the output because the prediction at time step 1 already covers A, so A is not fed into the RNN for prediction. Then similar things happens at time step 3 when B is available. At time step 4, when C is the new event, the tokenizer realized that ABC should be replaced using 3, and thus report 3 as the symbol, as the output symbol. Also, because the previous prediction 3 is already exhausted, so we feed this new token, the 3, into the RNN for prediction, and it predicts D. At time step 5, A is a new event because the previous prediction is wrong, so A is fed into RNN for a new prediction at this time. RNN predicts B. Then in the time step 6, you get B. Tokenizer produces B as well, and then this B symbol will be fed into the RNN and predicts the F. The scene becomes more interesting at time step 7 when C comes. Tokenizer again realizes that ABC should be combined together into a symbol and thus outputs 3. However, 3 cannot be fed into the RNN model immediately because the model is not in the right state. The model state is already updated using the symbol A and B at prior steps. So we have to revoke these state changes. And we replace H6 with H4, that is a hidden state at time step 4. so that we can fit 3 into the model, and then the model can give us the right prediction. Until now, we have covered the 2 challenges and the solution to each of the challenge. Next, we will talk about the experiments. In our experiment, we evaluate the algorithm using 16 real-world data sequences, including program function calls, memory traces, and system logs. Each of the sequences contains 500,000 events, where the first 50% of the events are used for offline model training, and the rest is used for model inference. The RNN model we use is a typical model contains an embedding layer with 256 in dimension, a GRU layer with 1024 units, and a fully connected layer as the output layer. Our experiment answers 3 questions. First, can the new algorithm keep the accuracy satisfactory? Recall that we allow users to specify the accuracy drop they can tolerate. We experiment with 2 accuracy drop rate that is 0% and 1%. We compare our method, which gives you prediction based on compressed streaming inputs, and the baseline method that predicts the next event directly based on the streaming input. And obviously, the answer is yes. The method can keep your original accuracy. The second question is, what is the prediction speedup we can achieve? This table lists the speedup results for 4 of our 16 benchmarks. Overall, we can decrease the inference time by up to more than 1,000 times. The last question is about prediction scope. This table reports the average prediction length of 4 of our benchmarks. Overall, the prediction scope can cover an average of up to 7,000 future events in one single prediction. It is also worth mentioning that given the same prediction scope, the traditional approach will suffer from up to 54% accuracy drop. So in conclusion, this is the first work that integrates data compression into RNN to speed up RNN inference and enlarge the prediction scope. The proposed compressed learning approach implies a novel learning paradigm for sequence modeling. It addresses the tension between compression rate and inference accuracy through lowering and overcomes the myopic nature of online tokenization through rollbacks. The compressed learning unlocks the potential of RNNs for many real-time applications. Thank you.